Welcome to the Deep Dive. Today we're tackling something truly fundamental, an invention that, well, it's everywhere, in literally every piece of modern tech you own. Think about the device you're listening on right now, your phone, your computer, even, the systems in your car. They all rely on this one thing. But here's the catch. Most people have never actually seen one. Not really.
That's right. It's sort of the ultimate invisible engine, isn't it?
Exactly. We're talking about the transistor. If you ask me point blank, what's the single most important invention of the 20th century? I mean, it's got to be this, right?
It's always in the top contenders, absolutely. Often cited as the greatest. It's this tiny semiconductor device, and its job is essentially to amplify or switch electrical signals. Simple idea, profound impact.
It's the basic building block, the absolute foundation.
Precisely. And our mission today really is to unpack how this minuscule component, basically using a tiny bit of electricity on one part to control a much bigger flow on another, how that simple function paved the way for, well, everything digital, the entire modern world, really.
Okay, so let's dive in. It didn't just pop into existence in 1947 at Bell Labs, fully formed. I was reading the background. And the idea itself, the concept, is much older.
It is, yeah. And it's a fantastic example of theory kind of leapfrogging the practical ability to build something. The idea for what we now call a field effect transistor, or FET.
Right.
That groundwork was laid way back in the 1920s. There was a physicist, Julius Edgar Lilienfeld. He actually filed patents for a device that works on the FET principle as early as 1925.
1925.
Right.
So he basically had the blueprint for a solid-state switch way back then.
Right.
But couldn't build it.
Exactly. The problem was materials. To control electricity at that scale, you need semiconductor materials that are incredibly pure, like unbelievably pure.
And they just didn't have that kind of refinement back then.
Not even close. In the 20s and 30s, purifying silicon or germanium to the necessary degree, it was impossible with the technology of the time. So Lilienfeld had this brilliant idea, a solid-state device to replace the clunky vacuum tubes. But he was stuck.
The invention had to wait for the material science to catch up, essentially.
That's a perfect way to put it. Physics and chemistry needed to advance first.
And when that breakthrough finally happened, that moment in 1947, it wasn't just one lab working in isolation, which I found really interesting.
No, it's key context. The first working device, the one that gets the most press, was the point contact transistor, demonstrated late 47 by John Bardeen and Walter Brattain at Bell Labs.
And William Shockley was involved too, right? He was their group leader.
Yes, Shockley was the group leader and later developed the much more robust junction transistor. The three of them shared the Nobel Prize in '56 for their work.
Got it.
And just as a side note, the name transistor, that came from John R. Pierce, another Bell Labs guy. It's a mashup of transresistance, basically describing how it works.
Transresistance. Okay, makes sense. But you mentioned it wasn't just Bell Labs.
Right. And this shows how right the idea was. Only about 6 months after the Bell Labs team announced their success, completely independently, a team in Paris.
In Paris?
Well,
Seriously?
Yeah, Herbert Maturet and Heinrich Welker, they developed their own working point contact transistor in June 1948. They actually called it the transistron.
The transistron. That's amazing. So the idea was just sort of in the air once the material science problems were cracked.
It really seems that way. The time was right.
And this was such a huge deal because before this, all electronics that could amplify or switch signals, they relied on something very different, very fragile.
Oh, yeah. The vacuum tube, specifically the thermionic triode, invented way back in 1907 by Lee de Forest.
And these were the standard for radios, early computers.
Everything. They enabled long-distance phone calls, radio broadcasting, radar, critical stuff. But man, the downsides were huge. They were literally glass tubes, like light bulbs.
Fragile.
Incredibly fragile. Drop one, it shatters. They were bulky, took up a ton of space. And the big one, they needed a heater, a hot filament inside, just to work.
Like an old light bulb filament.
Exactly. Which meant they consumed a lot of power, generated a lot of heat, and you had that warm-up delay. You couldn't just instantly turn things on.
I remember hearing about early computers like ENIAC taking up entire rooms, needing massive air conditioning. Mostly because of the heat from thousands of vacuum tubes.
That's precisely it. Thousands of these hot, fragile glass bottles, constant maintenance, huge power draw. Just keeping them running was a major engineering feat in itself.
So along comes the transistor in 47, 48. Solid state, no moving parts, no filament. What were the killer advantages, the things that made everyone immediately see this was the future?
Well, it addressed pretty much every single drawback of the tube. It was a revolution. Okay, so first, size and weight. Transistors are tiny, microscopic eventually. Equipment instantly shrank. Think room-sized computers becoming eventually pocket
Right,
calculators.
miniaturization, that's number one.
And number two, no heater filament. That's massive. It means no warm-up time, drastically lower power consumption, orders of magnitude less, and they weren't constantly burning out like filaments did.
Much more reliable then.
Much more. Third, low operating voltages. They could run happily on small batteries, unlike tubes that often needed hundreds of volts. This opened the door to portable electronics.
The first transistor radios.
Exactly. And fourth, ruggedness. Being solid state, they're inherently resistant to shock and vibration. You could drop a transistor radio. You couldn't drop a vacuum tube radio.
Okay, so smaller, less power, no warm-up, runs on batteries, tough as nails. It sounds like a total knockout. Game over for the vacuum tube, right?
Mostly, yes, it was a paradigm shift. But, technology transitions are rarely absolute, especially at first. There were, and in some very niche cases still are, areas where tubes had the edge.
Really, even today. What were the transistor's limitations, or where did tubes still win out?
Well, especially early on, transistors couldn't handle very high power or very high frequencies as well as specialized tubes could. And even now, for extreme applications, think really high power radio transmitters or certain types of microwave devices like traveling wave tubes used in satellites.
Satellites still use tube tech.
Some specialized types, yes, because they can handle immense power levels and frequencies where solid-state devices might struggle or be prohibitively expensive. Also, tubes are inherently much, much more resistant to things like electromagnetic pulses or radiation.
Ah, like EMPs from nuclear events, or
Yeah.
even just space radiation.
Exactly. Transistors are quite delicate when it comes to sudden voltage spikes or radiation. Think about static electricity. You shuffling across a carpet on a dry day can generate enough static to zap and destroy a sensitive transistor if you're not careful. Cosmic rays in space can flip bits or even cause permanent damage.
Right, I've heard about electrostatic discharge, ESD, being a big problem in electronics handling.
It's a huge concern. Vacuum tubes, being basically chunks of metal in a vacuum, are electrically much more robust against that kind of abuse. They laugh off things that would kill a transistor instantly.
Okay, that's fascinating. So, not a total wipeout, but for 99.9% of applications, the transistor's advantages were just overwhelming.
Overwhelming, yes. The stage was set for the solid-state revolution.
So we know why it took over. Now, let's get into the how. How does this tiny thing actually control electricity? You mentioned it has kind of two main modes, two jobs it does.
That's the core of it, yeah. It has this dual personality that lets it underpin both the digital world and the analog world.
Okay, mode one.
Mode 1 is its job as a switch. This is the absolute bedrock of all digital computing. In this mode, you basically force the transistor to be either fully on, acting like a closed switch, almost a short circuit,
Letting current flow freely.
right, or fully off, acting like an open switch, almost an open circuit, blocking the current.
On or off, 0 or 1, binary.
Precisely. That binary on-off function is what allows us to build logic gates, AD gates, or R gates, not gates, the fundamental components that process the ones and zeros of computer language. Every calculation your computer does boils down to billions of these tiny switches flipping on and off incredibly fast.
Okay, so that's the digital side. Computers, logic, what's the other mode?
The other mode is as an amplifier. This is crucial for the analog world dealing with signals that vary continuously, like sound waves or radio waves.
Not just on or off, but shades of gray.
Exactly. In amplifier mode, a small change in the input signal, maybe a tiny current or a small voltage at the control terminal, produces a much larger but proportional change in the current flowing through the main part of the transistor.
So it boosts the signal.
It boosts the signal's power or amplitude, yes. Think about the weak signal picked up by your phone's antenna from a distant tower. A transistor amplifier boosts that tiny signal so your phone can process it. Or think about a concert amplifier taking a small signal from a microphone and boosting it enough to drive huge speakers with hundreds of watts.
Wow, okay. So switch for digital, amplifier for analog. Same device, just used differently in the circuit.
That's the beauty of it. Incredible versatility from one basic component.
Now, things get slightly more complex because there isn't just one type of transistor, right? The sources mention two main families based on how they're controlled.
Yes, that's important. The very first working transistors, the point contact ones and Shockley's improved junction transistor, belong to the bipolar junction transistor family, or BJT.
BGT. Okay.
With BJTs, the key thing is they are current controlled. A small current flowing to one terminal, called the base, controls a much larger current flowing between the other two terminals, the collector and the emitter.
So current in controls current out.
Basically, yes, that was the first type to be widely manufactured and used.
But then there's the other family, the one Lilienfeld envisioned back in the 20s.
Right, the field effect transistor, or FET. The terminals have different names here: gate, source, and drain. And the crucial difference is that FETs are voltage controlled.
Voltage controlled. How does that work?
Instead of a current, you apply voltage to the gate terminal. This voltage creates an electric field, hence the name field effect, that either allows current to flow between the source and drain or pinches it off, restricting or blocking the flow.
So no significant current flows into the control terminal, the gate. It's just the voltage level there that does the controlling.
Exactly. The gate draws almost no current, which can be a big advantage in many circuit designs, especially for low power consumption and digital logic.
Okay, so BJT is current controlled, FET is voltage controlled. Two different ways to achieve that switching or amplifying action.
Correct. And while BJT's got the ball rolling, it's a specific type of FET that absolutely came to dominate the modern era.
Yes. This is where the story shifts again, isn't it? To the undisputed champion of the transistor world.
It really is. We need to talk about the MOSFET. That stands for metal oxide semiconductor field effect transistor.
MOSFET. That's the one you see mentioned everywhere in relation to computer chips.
Absolutely everywhere. The MOSFET is, without exaggeration, the most important electronic device invented in the second half of the 20th century. It is the essential building block for virtually all modern digital electronics microprocessors, memory chips like RAM and flash, image sensors, everything.
So what made the MOSFET so special? Why did it overtake the BJT and other early FET types?
It comes down to a few key things enabled by advances in materials, particularly silicon processing. The MOSFET concept itself was demonstrated back in 1960 by Mohammed Atallah and Don Kong, again at Bell Labs.
Bell Labs again.
Yeah.
They were really on a roll.
They really were. Their work built on earlier breakthroughs in the late 50s, particularly understanding how to create a very stable insulating layer of silicon dioxide on the surface of silicon. This oxide layer is the O in MOSFET, and it's absolutely crucial.
Why is that oxide layer so important?
Because it perfectly isolates the gate terminal from the main current-carrying channel. This means the gate draws essentially zero current, making it incredibly efficient for switching. More importantly, this structure turned out to be fantastically scalable. You could make MOSFETs incredibly small and pack them incredibly densely onto a silicon chip.
Ah, scalability and density. That sounds like the key to modern computing.
That's exactly it. BJTs are harder to miniaturize to the same degree and consume more power in digital circuits. MOSFETs, especially a variant called CMOS, complementary MOS, became the foundation for low-power, high-density integrated circuits.
And this is where the numbers just start to get insane, right? The scale of MOSFET production is just hard to comprehend.
It really is. Prepare yourself. The MOSFET accounts for, oh wait for it, 99.9% of all transistors globally.
9.9%. So basically all transistors being made today are MOSFETs.
Pretty much. For every 1,000 transistors manufactured, 999 of them are MOSFETs. It's an almost complete monoculture in terms of sheer volume.
That's staggering. It's like saying 99.9% of all vehicles are one specific model of car.
It's even more extreme than that, really, because the total number is astronomical. The MOSFET is officially the most manufactured artificial object in human history.
Most manufactured object, more than screws or bricks or...
More than anything. By 2018, estimates put the total number of MOSFETs ever manufactured at over 13 sextillion.
13. Sextillion. That's 13 followed by how many zeros?
21 zeros. 13 billion. Billion.
Wow. Okay. My brain just stalled trying to picture that number.
It's almost meaningless, isn't it?
Mm.
But it highlights the power of mass production and scalability. Why so many? Because modern chips are packed with them. A state-of-the-art microprocessor today, like the one in a high-end computer or server, it might contain as many as 134 billion transistors.
134 billion on a single chip. A piece of silicon, maybe the size of a postage stamp.
Or even smaller, like a thumbnail. That's the power of MOSFET scaling and integrated circuit manufacturing. The ability to reliably make and connect billions, now heading towards trillions, of these switches on one tiny die is what drives Moore's law and the whole digital revolution.
It's not just inventing the switch, it's figuring out how to make trillions of them work together perfectly.
That's the real magic, yes. The manufacturing science is just as incredible as the initial invention.
Okay, so we have this dominant MOSFET, but there's still diversity, right?
Yeah.
You mentioned BJTs are still around, other FIT types,
Yeah.
JFs of FinFETs,
Mhm.
using different materials too, not just silicon.
Absolutely. While MOSFETs rule the digital world, other types have their niches. BJTs are still great for certain analog amplifier circuits or high-power switching. JFETs, junction FETs, are used in sensitive analog applications. Newer structures like FinFETs are how manufacturers are pushing scaling even further in the latest chips. And materials like germanium, the original transistor material, gallium arsenide, silicon carbide, gallium nitride, they offer advantages for high frequency, high power, or high temperature operation where silicon struggles.
So a whole ecosystem of different transistor types and materials for specific jobs, which must make things confusing for engineers, especially when they're dealing with individual discrete components, not just chips with billions inside.
It could be chaos, yes. Imagine a drawer full of tiny black components with just cryptic numbers on them.
How do they keep them straight? If
Yeah.
you're building a circuit on a breadboard and need a specific type of transistor, how do you know what's what? Is it just memorizing manufacturer part numbers?
Thankfully, no. There are standardized naming conventions, primarily based on region of origin, that give you a lot of information right away from the part number prefix. It's actually pretty neat insider knowledge if you ever tinker with electronics.
Okay, lay it on us. How do these codes work?
There are three main systems you'll encounter. First, the US system, managed by JDGIS. For discrete transistors and diodes, devices usually start with 2N.
2N, like the classic 2N 2002-32 or the 2N 3904.
Exactly. Those are ubiquitous general-purpose NPN BJTs. The 2N tells you it's a JDE registered semiconductor with 3 leads. The technically 2PN junctions.
Okay, so 2N means American Standard 3-lead device. What about other regions?
Then you have the Japanese JIS standard. Their prefixes start with 2S.
2S.
Right. And the letters that follow tell you the type, like 2SA or 2SB are usually PNP BJTs, 2SC or 2SD are NPN BJTs. 2SJ is a P-channel FET, 2SK is an N-channel FET.
Ah, so 2SC 1815, another super common one. That's a Japanese NPN BJT.
Precisely. And often, to save space on tiny components, manufacturers will drop the 2S prefix. So a transistor might just be marked C1815, but an engineer knows that C likely implies a 2SC NPN BJT.
Clever. Okay, US is 2N, Japan is 2S. What about Europe?
Europe uses the Pro Electron, or ECA, standard. This one uses 2 letters, sometimes followed by a number. The first letter tells you the semiconductor material. A means germanium, B means silicon.
A for germanium, B for silicon.
Got it. The second letter tells you the application. C is usually for small signal general purpose audio frequency transistors. D is for power audio frequency transistors. F is for small signal radio frequency transistors.
So I see something like BC 548.
Instantly, you know. D means silicon, C means small signal audio general purpose. It's a very common NPN BJT used in hobbyist circuits. Or if you saw an 8162, that would be A germanium, D power audio, likely an older PNP power transistor.
That's actually really helpful. It brings some order to the potential chaos of all these tiny parts. 2N, 2S, BC. Little codes pack in a lot of info.
Without these standards, identifying and substituting parts would be a nightmare for designers and repair technicians.
What an incredible arc we've traced. From Lilienfeld dreaming it up in 1925 to Bardeen, Bratton, and Shockley making it real in 47.
The parallel work in Paris.
Right. The transistorin, then displacing the big, hot, fragile vacuum tubes.
The rise of the BJT, then the FET, and finally the utter complete dominance of the MOSFET.
To the point where we've made 13 sextillion of them. It's just, yeah, mind-bending.
And the impact goes beyond just electronics. Think about machinery control. It used to be all complex relays and mechanical timers.
Now you just slap in a tiny microcontroller chip packed with millions or billions of transistors, write a few lines of code, and you're done.
Exactly. It's often far easier, cheaper, more reliable, and much more flexible to use a programmed microcontroller than to design a purely electromechanical control system these days. Transistors made software eating the world possible.
So we end up here, this tiny switch, refined and shrunk beyond belief, running essentially everything, 134 billion on a chip. What's the big takeaway, the final thought to leave our listeners chewing on?
Well, we've mastered the switch itself, haven't we? On or off. Simple. We've mastered making them incredibly small and incredibly numerous. But the real frontier now, the mind-bending challenge, is the organization.
Organizing those billions, soon trillions, on a single chip.
Precisely. As we push towards maybe trillions of transistors on one device, we're hitting serious physical limits. Quantum effects start messing things up when components get down to just a few atoms across. Heat density becomes a nightmare. How do you connect them all? How do you design and verify something that complex?
Can we just keep shrinking, or do we need a totally new approach?
That's the multi-trillion-dollar question, isn't it? Is the future just smaller MOSFETs, maybe built with new materials or 3D stacking? Or do we need fundamentally different computing architectures, neuromorphic computing, quantum computing, that move beyond the simple on-off switch paradigm?
How long can we keep cramming more and more onto these chips before we hit a wall? We just can't engineer our way around.
We don't know, but figuring that out, managing that almost unimaginable complexity to keep the digital revolution going, that's the grand challenge driving electronics research today. It's not just about the switch anymore, it's about orchestrating the symphony of trillions.
A profound thought to end on. The tiny switch built the modern world, but managing its sheer scale is the next monumental task.
Couldn't have said it better myself.